Yeah, hello everyone. I am Bastian Schöneberg from CFX Berlin. For anyone who does not know our company yet, CFX Berlin is a specialist in numerical simulation. We distribute ANSYS, TwinMesh, FlowNex, and ParticleWorks and give trainings and support for the software. We also offer consulting and simulation services, which means that we use the software every day for solving engineering problems. So we can support our customers with first-hand experience. In the next 45 minutes, I would like to give you an insight into the modern design of electric motors, which means that we are using computer-aided engineering tools to accomplish this task. I will give an overview of common tools used in this process, and I will show an example of a thermal flow analysis of an induction machine. In the past, electric machine design has been seen as only an electromagnetic problem. But nowadays, this is a fast-moving field, so the design approaches had to evolve to keep up. The high power density of modern motors leads to electric machine designs that operate at the electromagnetic, electrical, thermal, and mechanical limits. Increasing competition requires shorter development cycles, with a strong focus on achieving highly optimized designs. Usually, the operation covers also a wide torque speed range, meaning that a high single operating point efficiency is not sufficient anymore. You probably know ANSYS as a provider for structural analysis tools. And indeed, this is how ANSYS started in the 1970s. These days, ANSYS offers engineering software for a wide range of applications. And electric motor design is one of those applications. The tools cover rapid design approaches like MotorCAD, to detailed analyses of magnetic, mechanical, and flow phenomena. In addition, the results of these analyses can be used in a system simulation to calculate the motor's behavior and interaction with other components like controls or power electronics. Let's start with a quick overview of ANSYS MotorCAD. ANSYS MotorCAD is the market-leading tool dedicated to the design and analysis of electric motors. It enables rapid and accurate electromagnetic, thermal, and mechanical analysis of radial flux machines across the full operating envelope. MotorCAD is designed and developed in close collaboration with expert electric machine designers and embeds a lot of engineering expertise. We have 4 design modules in MotorCAD. The EMAG module that allows the evaluation of electromagnetic performance based on predefined motor templates. The powerful therm module to predict thermal performance, like winding and magnet temperature, based on predefined cooling templates. The MAG module for evaluation of the rotor stresses caused by rotation. And finally, the lab module that is comparable to a test rig, where you can determine the motor's performance under different load conditions and duty cycles. Those modules are coupled, meaning that you can quickly and iteratively evaluate motor topologies and concepts. in order to optimize size, performance, and efficiency. For example, you can model the impact of your thermal design on the electromagnetic performance and losses, which in turn influence the temperatures in your machine. MotorCAD can handle all typical types of radial flux rotating electric machines. A brushless permanent magnet with inner or outer rotor, induction machines, synchronous and switched reluctance motors, a synchronous wound field, permanent magnet DC, and single-phase induction machines. Some of the designs are shown here on the right-hand side of the slide. With the electromagnetic module of MotorCAD, you can calculate torque, power, losses, voltages, currents, inductances, flux linkages, and forces. Those results are based on an analytical modeling approach combined with an embedded 2D transient FEA solver. The module offers an automated winding and slot cross-section editor. The designs can be input and calculated in minutes, allowing lots of iteration and a full exploration of the design space, so you can ensure optimal design decisions. At the same time, MotorCAD offers advanced calculations and modeling depth, like eddy currents in magnets and accurate AC winding losses. The thermal module is really a strength of MotorCAD. It is an industry standard tool for thermal analysis of electric machines with over 20 years of inbuilt experience for heat transfer and contact resistances, for example. You can calculate the temperature of the motor components in steady state and transient operating conditions. It allows for accurate modeling of thermal behavior within seconds of calculation. And it uses CFD, FEA, and empirical correlations for that. So it can help you understanding the main heat transfer path and develop opportunities to significantly improve the output of your machine. The thermal components of the machine are again template-based and cover all common types of cooling, from air ventilation over water jacket to oil spray cooling. The lab module of MotorCAD is a virtual testing laboratory for your motor. It uses the coupled electromagnetic and thermal module to create a detailed efficiency and performance map, thereby taking into account changing inductances and losses. And based on this map, you can plot peak torque speed curves as well as continuous operating torque speed curves. It automatically applies maximum torque amplitude control strategies to replicate the performance of a machine with inverter. A library of common duty and drive cycles can be used to optimize the design for maximum cycle efficiency. So MotorCAD offers a very fast template-based design approach with very good accuracy in performance prediction. However, there are more demanding tasks. For example, what is the influence of eddy currents and 3D effects on the performance? How can I optimize my motor with concurrent targets, weight, efficiency, torque ripple? How to design the internal air fan for better cooling. Or my customer criticizes noise and vibration. What could be the problem? How does the motor perform when part of the powertrain? To answer these questions, we clearly need an in-depth knowledge of our machine behavior. MotorCAD offers several interfaces to more specialized ANSYS tools. So it enables us to rapidly go from the design level to the deeper analysis level. We can export the whole motor design to Maxwell for further analysis in 2D or 3D. And this covers not only the geometry, but also material data, winding definitions, excitations, and boundary conditions. There's also a workflow for OptiSlang, which is a tool for doing design of experiments and optimizations. OptiSlang takes control over the MotorCAD software and runs an analysis of the motor design's response to changes in input parameters we chose. Based on this response, we can find optimal designs for concurrent optimization targets. We can also quantify the robustness of our design with respect to manufacturing tolerances, for example, changes in material properties or geometric tolerances. MotorCAD also has an FMU interface for ANSYS Twin Builder or other system simulation software. The standardized FMU output enables us to integrate the motor model in a system simulation in order to calculate the motor's behavior and interaction with other components of the powertrain. Finally, we can export the motor's geometry data to ANSYS Workbench via Design Modeler. Based on this model, we can perform the whole range of detailed multiphysics analysis that ANSYS offers. This includes mechanical simulation as well as flow analysis with, for example, Fluent. Those detailed results, say heat transfer coefficients, can be used to tweak the MotorCAD model to be even more accurate. Let's have a closer look at the in-depth analysis of electric machines, starting with electromagnetic field calculation. ANSYS Maxwell is a general purpose, low frequency electromagnetic solver. Low frequency means that all changes in current immediately change the field. So we neglect electromagnetic wave propagation. This assumption is okay if your geometry is much smaller than the wavelength of the signal you have. For higher frequencies in the megahertz region and above, there are special solvers like HFFS that are used in antenna design, for example. The geometry basis in Maxwell can be an import or from CAD. There are, of course, interfaces to the major CAD software packages. Or you can import the model from MotorCAD or RM Expert. Then it's fully parameterized. RM Expert is another motor design tool included in Maxwell, but has less features than MotorCAD, and nowadays is used primarily for model creation for Maxwell. And finally, of course, you can start from scratch and build your own geometry model within Maxwell. Then, of course, it is also fully parameterized. There are several 2- or 3-dimensional analysis types available. depending on the physics you would like to model. Magnetostatic analysis, where current or permanent magnets are source of a magnetic field, like this lifting magnet. We also have electrostatic field calculation, which may be used, for example, in high voltage insulation applications. There is a DC conduction solver for modeling detailed current flow in inductors. And there are solvers for unsteady field behavior. The eddy current solver assumes that all signals are harmonic and is often used to calculate the inductance, for example, of such a transformer. The transient solver can handle all types of signals. It covers movement of bodies and all unsteady inductance and hysteresis effects. So that is the one we normally use for calculating electric machines. But it is also the one that requires the highest computational effort. When staying in 2D, typical calculation times for rotating machinery are half an hour up to a day, depending on the accuracy you want to achieve and the computer resources you have. Maxwell has an automated mesh refinement that is solution-based. The mesh is locally refined until the error in field energy is low. So what are the strengths when calculating electric machines with this tool? First of all, we can include 3D effects. This is particularly important when the axial length of the machine is short, like in torque motors. Then we have advanced material modeling that allows us to include nonlinear effects, hysteresis, demagnetization effects, and frequency-dependent core losses. We can also model transient effects that can be caused by the electric circuit around the motor or by non-cylindrical motion, like eccentricity or by variable speed. There are also phenomena that need a coupled calculation between different physical areas. Examples are magneto-vibroacoustic effects and structural stress caused by magnetic forces. For these applications, we can couple Maxwell with ANSYS Mechanical. Another common task is to calculate the interaction between electromagnetics and temperatures in the machine. This can be done with mechanical if only conduction through solids is important, or with ANSYS CFD if also the flow is important, which is the case in most motors. The ohmic losses and core losses calculated in Maxwell are transferred as heat sources to the flow calculation. The resulting temperature field from CFD, which you can see here, can then be mapped back to Maxwell again. And that way we can iteratively approach the coupled solution. Now I will show some details on mechanical and fluid dynamic tasks. ANSYS Mechanical is a general purpose structural mechanics solver. It can be used for stress analysis under static and dynamic loads and also for acoustic analysis. When used for electric motors, we often assess the topic noise, vibration, and harshness. That can be a simple modal analysis to determine the eigenfrequencies of the parts of the machine and the assembly. Or we transfer frequency-dependent loads from EM because loads can change the eigenfrequency. If we are also interested in the amplitude of these deformations and the resulting mechanical stresses, we need to calculate the system's answer to prescribed excitations. And that could be, for example, an electromagnetic force. The oscillations of the structure causes noise. Acoustic simulations based on dynamic deformations can predict the sound pressure levels outside the machine. And finally, vibroacoustic post-processing is available by means of a waterfall plot. The color shows the acoustic amplitudes for a given frequency that belong to certain machine speeds. It helps us in determining the noise that occurs for different machine loads. When it comes to cooling of electric machines, we soon arrive at CFD. ANSYS offers two general purpose computational fluid dynamics solvers. The market leaders, CFX and Fluent. Both are well validated and have a huge model breadth. The main application for CFD in electric motors is the thermal management. We can model the distribution of heat fluxes given the losses from EM as heat sources, and we can calculate the resulting temperatures. Doing so, we can take into account the conduction through solids, the convection through fluid, or even radiation effects. All types of cooling can be investigated. Air cooling with through or self-ventilation, or blown over, or natural convection. Water and oil cooling by jacket, or wet rotor, or spray cooling. We can, of course, also calculate heat transfer coefficients for the thermal network tools like MotorCAD. On the next slides, I will show you a detailed analysis on the cooling of a three-phase asynchronous motor. With a rated power of 400 kilowatts, the main application is in cargo loading bridges. Those calculations here were done for AEM, a German manufacturer of electric motors and generators. The aim was to benchmark the accuracy of the CFD calculations, and therefore the results were validated with measurements of temperatures and flow velocities. The first step of every CFD calculation is the geometry preparation. In this case here, the starting point was a CAD data provided by the manufacturer. The inner parts of the machine are completely encapsulated. Basically, we have two cooling airflows. Inside, there's a fan mounted on the shaft, causing circulation through the cooling channels in the housing and back through the axial rotor cooling ducts. For improved heat transfer, there is a second fan mounted on the outer part of the shaft, providing airflow over the cooling ribs here. This geometry model contains a lot of details that are not relevant for the results, but would cause us a lot of additional computational effort. So we needed to clean up the model, for example, by removing screws and by substituting the bearings with simple blocks of equivalent thermal properties. The second step in CFD is the mesh generation. For complex geometries, we usually combine different element types and meshes. Those are created for the solid bodies as well as for the fluid regions. Care has to be taken when defining the mesh interfaces and thermal contact resistances between the bodies. Here, the automatic contact detection capability of the ANSYS meshing solution saved us a lot of work. Overall element number was 17 million. So we are dealing with a medium-size mesh here that has refinements between the outer cooling ribs you can see here, and in the air gap between rotor and stator. The third step is to define physics and boundary conditions. The calculations were done with periodic assumptions in the inner parts of the machine and the outer fan. As you know, the rotor and stator are made of laminated steel, which leads to anisotropic thermal conductivity. This is shown in the sketch here. The axial heat transfer in that region is reduced to 10% of the solid steel value. So it is important to include this in our calculations. Another aspect is the modeling of the end windings. Those are usually quite complex structures and can look very different from application to application. Here, we did not calculate the flow through the end windings in detail. Instead, we used a surrogate model, a so-called porous medium approach, where we predefine a pressure loss coefficient and a heat transfer coefficient for this flow region. These coefficients have been estimated analytically, but they could also be obtained by measurements. Another important part of the physics definition are the losses of the machine that are heat sources for our calculation. First, we have electromagnetic losses that were estimated or calculated by the manufacturer. Core losses occur in stator back and stator teeth, as well as in the rotor elimination here, this orange part. Ohmic losses occur in the copper parts, stator slot and end winding, rotor cage. As you can see, we did not resolve each cable in the winding. Instead, we use a solid block with equivalent thermal properties. In addition to these EMAG losses, we have other kinds of heat sources. First, the bearing friction that was estimated here, and the fan power, which is part of our flow solution. So it is automatically included as a heat source. Now that we have defined all physical parameters, it is time for the computer to do the number crunching. We are solving for the steady state solution, that is the state of thermal equilibrium. While the solution is progressing, we monitor the key output parameters of the simulation. For an electric motor cooling simulation, that are, of course, temperatures, but also shaft power, as shown here. The solution showed some small fluctuations due to detached flow areas and moving eddies, but basically we arrived at a steady state result. The global balances are another criterion for judging convergence and were fulfilled within a 1% error here. The computer memory needed for the calculation was about 45 gigabytes, and the solution process took about 30 hours on 24 cores. This calculation was done some years ago. Nowadays, we can have, for example, 128 cores in such a 2-unit rack server system, meaning that this run could be done in a few hours. In the post-processing step, we can finally have a look into the calculated solution. Let's start with the flow outside through the cowling. Due to the direction-independent fan design you can see here, we do not have a perfect flow, as can be seen in the areas of flow separation at the blades. But the fan is producing a flow over the housing, and roughly 80% of the air enters the gaps between the cooling ribs. The rest of the air remains with swirl and escapes to the environment. When looking at the flow field inside, we can see that air calculation or air circulation works. So hot air is transported from the hot center of the machine through the inner fan to the outer air ducts, then in axial direction to the right side here, and back to the center to close the circle. But we can also see a bypass flow through the porous end winding that is situated next to the fan here. Here you can see the temperatures of the inner air, the motor solids, and the outer air. In a no-load condition, the temperature level is quite low. The hottest part is the bearing on the right side with about 60 degrees Celsius. In case of nominal load with higher losses, especially in the rotor copper, we get much higher temperatures. And we can see that the flange side end winding on the right side here is much hotter than on the left side where the fan is sitting. The reason is that the bypass flow we have seen just a moment ago flows through the end winding and provides some cooling. In this project, we had the luck that measurement data was available. So we were able to validate our simulations. Here we can see a comparison of the thermal image of the machine casing at no load. It shows good agreement with our CFD results. Only the bearing on the left side here, it is a little bit too hot in our simulation. So I think the friction we estimated there was just too high. Another measurement aimed at the air ducts in the casing. You can see them here. You can see that the calculated temperatures only differ from the measured values within some few kelvins. It shows that CFD calculations can help to understand the flow inside the machine, and that they can also be used to quantify the cooling performance. The detailed analyses we just saw help us in understanding the motor's physical behavior. But of course, the motor will be used in a certain application, and its actual performance will depend on other components that are connected, forming a dynamic system. ANSYS also offers simulation tools to investigate these interactions. This tool is named ANSYS Twin Builder. First of all, a digital twin is just the software representation of a real-world system or system component. So ANSYS Twin Builder is used to create such a twin. Originally, it was a pure system simulation tool named Simplora. By adding interfaces to industrial Internet of Things platforms, the software is now able to send and receive operational data of the physical counterparts of our digital twin. And that enables lifetime prediction, for example, and preventive maintenance based on simulation. Here we will focus on the system simulation aspect. So what we can do is a multi-physics simulation of whole systems that consist of multiple components. And one of those components could be our electric motor. Each component is a black box and is characterized only by its behavior when input parameters change. The input and output parameters can come from different physics areas, for example, electrical and thermal. And the function connecting these parameters can be very complex. Here you can see an overview of such a system simulation. The system model in the center here is made of different predefined component types. For example, system library components that are well known. For example, electrical switches or power electronics or other modeling domains and languages. You can see some inbuilt components here. Another form of component is a reduced order model. These reduced order models simplify 3D physics and can be derived from test data or from detailed simulation as seen before. Twin Builder has the capability to extract ROM data of different complexity levels. Finally, we can also do a co-simulation with external solvers to get a components response. Once we have done our system simulation, we can encapsulate this system knowledge into a functional mockup unit, FMU, or a twin model for further use in external programs like IIoT platforms. Let's have a look at an example of a brushless permanent magnet DC motor. This is the project schematic of a system in Twin Builder. It has two components representing two aspects of motor design, electromagnetic and thermal. Each component has input pins on the left side and output pins on the right side. The sum of the pins are connected to the other component. showing that these components interact with each other. For example, the output of winding temperatures here and magnet temperature of the thermal component is connected with the corresponding input pins of the EM component. This way we create a coupling between the components. The inputs for the magnetic component are here time-dependent shaft speed and torque demand, while having a constant DC bus voltage for the windings. The inputs for the thermal component are constant ambient temperatures and water feeding temperature, as well as constant water jacket flow rate. As a result of this analysis, we get the information how hot the different parts of the motor will get with time, based on the duty cycle we had defined. This type of analysis would be possible in MotorCAD, within MotorCAD itself, but in Twin Builder, we are free to attach any other component to the system. That could be motor controls, power electronics, other parts of the powertrain, or battery characteristics, for example. So that's it from my side. I hope that I could give you some insights into the modern engineering tools for electric machines. Let's see how's our time. Do we have some time for questions? Are there any questions from the audience?
Hi, you have two questions in question panel.
Yeah, I can see them here.
Okay.
What is meant by solution-based mesh? I think you refer to the slide where I showed the capabilities of Maxwell. Let's see. I think this slide here. Here you can see a cross section through this lift magnet geometry. And in Maxwell, we start with some initial mesh that is automatically created. We can also define some refinements based on geometry, for example, in regions where we know that are important to us. But when we start the calculation, the solver will look on the field distribution and will estimate an energy error in the magnetic field. And where this error is high, the mesh will be refined by a user-given refinement factor in each step. And so we have multiple passes that are performed one after another, and in every pass we have a mesh that is refined. And this process goes on until we have a mesh-independent solution. So I hope that answered your question. Yes, so how the eddy current losses are calculated in 3D permanent magnet synchronous machine model. I think this refers to the MotorCAD electromagnetic modeling. Yeah, those eddy losses are actually created or calculated using the 2D FEA solver. Typically, we assume that we have harmonic fields, and based on this harmonic assumption, we calculate the eddy current losses in the conducting regions. You know, also magnets have some electrical conductivity, so we can also have eddy currents in the magnets here of the synchronous machine, for example. Spray, yeah, I have another question. Spray cooling with ANSYS CFX is possible. Yes, and yeah, examples are the question here. This is really not an easy task to do. This is of course true. One first problem in those spray cooling calculations is, for example, the properties of the spray. Those are very microscopic effects that we have when the oil leaves the nozzle, and this is really some type of current research how to efficiently do this. But once we have this this spray properties, for example, the particle size distribution, we can use this to create a particle injection region in CFX, and then we can have a look at where does the oil go. It is not so easy to calculate the heat transfer when those particles when they splash onto solids and so on. This is right, but we can see if the oil distribution is okay and where does the oil go, especially when we have additional airflow and rotation in the machine. So this interaction can be modeled. Yes, if you have other questions, please let me know. Maybe I show my email address here again. Just contact me, and yeah, with that, I think I will hand over here to the next one. Thank you very much.
Thank you. Okay, good morning to everybody. I'm Francesco Franchini, and I am the technical manager of the team that in Engine-Soft is in charge of process integration and multidisciplinary optimization activities. And today I would like to report to you one of the experience of our customer, Bonfiglioli, about the multidisciplinary optimization of an induction and electric motor. This is the agenda for the presentation. We will start with a short introduction about what numerical simulation can do for us, how we can get advantage by combining cost and performance evaluation together into a multidisciplinary parametric approach, and some words about the multidisciplinary optimization methodology, what are the main pillars and how we can implement it. Then we will move through the industrial application. Finally, I don't know if there will be enough time for the online question answer session, but anyway, you can send me offline question after the webinar if you want. That is my mail address, and it will be a pleasure to answer them. Okay, we can start. Nowadays, the virtual models and simulation can help us to evaluate performances, generally speaking, technical, all kind of performances like stress, thermal management indicator, pressure safety factor, and some other. And additional to that, also performance like cost. The basic idea is that costs are designed into the product even from the first conceptual decision, or anyway during the development phase, and that are difficult to remove or to extremely modify them later. So the costs in that case are seen as an extended requirement, let me say, an important, equally important parameter in addition to the technical performances, technical requirement. By making the right design decision already during the conceptual phase, or anyway in the early stage of the project, it is possible to avoid unnecessary costs in the following phase. With unnecessary costs, I don't mean only the reduction of cost due to reduction of weight or a different manufacturing process, but also unnecessary cost due to the iterative action, iterative manual redesign due to a wrong initial decision. And in that case, the multidisciplinary parametric approach can help us because can allow us to consider different aspects, different discipline that insist on the development of my product, and we can consider probably interaction between different aspects just in the beginning phase. Another point is about the opportunity to be flexible, sorry, with respect to market change and new requirements. And with new requirements, I mean also the vertical or customized solution for our customer. So being able to rule all these points is for sure a key to success. But how we can do it is not so simple, effectively. On our side, we have identified three main keywords. First of all, we have to be able to analyze and catch our development process. Then we have to define parametric models in order to handle the right leverages to get the best performances, the best compromise solution. And last but not least, the automation of the process, which increase our efficiency and speed up our development process. This give us a most comprehensive decision-making process to drive us to the final choice, the best final choice. What about the MDO? ModFrontier is our platform, is the platform used in this industrial application as MDO platform. ModFrontier is an integration platform that provides a straightforward coupling with third-party engineering tools like CAD, but CAE tools, but also Excel, MATLAB, in-house code, enables the automation of design simulation process and facilitates the analytic decision making, the final choice. Just a few words about the MDO approach. The process integration, automation, and parametric analysis or optimization are the three pillars that sustain the MDO methodologies, okay? The multidisciplinary parametric approach. If you lose one of the pillar, the table, let me say, the table cannot be balanced and falls down. So we need of all three aspects, process integration, automation, and optimization. So the process integration allow you to consider the system or part of the system as a whole. In this way, we can improve our product, our system, taking into account different discipline, different model that can contribute to our solution, and taking advantage of potential interaction among them. Like in the example in the slide where we put a model geometry, a pre-processing model, a meshing model, and then a couple of solver for the structural and fluid dynamics part analysis. The second pillar is the process automation. Once the process is defined, it can be also automated by an automatic engine, for instance, which iteratively can run the entire process from the start to the end without manual interaction. So automatically I can rebuild my geometrical model following some modification, then a new meshing model, and then I can run automatically my solver, the solver that I usually use in my development process, like in this case, structural and fluid dynamics solver. At this point, the final step, the parametric analysis or optimization to improve our performances. The automatic engine can become a clever engine. So you can use, instead of the automatic engine, a artificial intelligence, an optimization algorithm, which can evaluate our performances like stress, uniformity, or flux, and then change length and change, the output, our input parameter accordingly with this strategy. How we can translate all this process, all this stuff in a workflow, in a useful workflow inside a MDO platform is really simple. The process inside our platform can summarize it with a simple workflow where you can find again input parameter and output parameter with their objective and constraint. Let me say logic flux that include all tools that you usually use in your day-by-day development design activities. And then you have to define a strategy. Strategy, it means that you can run just a single design, a single shot to evaluate some modification, or you can run design of experiment in order to evaluate sensitivity analysis between input and output, or you can run a complete optimization loop in order to find out the best compromise solution. Coming now to the industrial application, I would like to thank again Bonfiglioli to provide us these interesting activities. The objective of the activity is the redesign of the current electric asynchronous motor of Bonfiglioli. This product has already sold at the time of the activity, has already sold in the European market, but they decided to propose the similar solution for the North American market. But unfortunately, the value of efficiency for a different sizing, a different power of this electric motor product doesn't respect the regulation requirement of North American market. Doesn't satisfy this ULCSA certification, the North American certification. So one of the main goals was the improvement of energy efficiency, together with a new but recognizable aesthetic design and cost optimization in order to have a good quality price ratio for the new market, a good compromise between performances and cost, let me say. The first step is the definition of design constraints. The design constraints coming partially from electromagnetic and thermal requirement, so from design requirement, let me say, and partially from aesthetic needs in order to maintain a certain kind of look for our induction motor. After that, a workflow for the optimization process has been built, integrating the typical technologies used by Bonfiglioli in their development process. In this case, flux for the electromagnetic evaluation and MotorCAD for the thermal management evaluation. Then geometrical information has been extracted as well from the workflow to evaluate cost performances. In that case, MotorCAD at the time of the activity was a standalone product. It's not inside ANSYS Workbench. Otherwise, we can use the ANSYS Workbench direct integration node in order to integrate this product inside ModFrontier. point here. In that case, the integration has been performed by means of Excel file, because both software can use this solution to extract the input and output information. And so the first solver integrated was the Flux for the electromagnetic evaluation, then MotorCAD for the thermal management evaluation, and to extract also geometrical information. So in order to effectively carry out the optimization process, the following analyses were performed. We started with a design of experiment analysis in order to perform a sensitivity analysis. So a design of experiment, a design of experiment set up in order to perform a sensitivity analysis that allow them to evaluate what were the most important variable in order to achieve their goals. And so this allow to decrease the number of input variable, but this allow also to review the input variable range for the optimization, to speed up the optimization process. After that, now we know what are the best leverage to achieve our goal, that are cost and efficiency, and we can start with the optimization evaluation, optimization loop. And in that case, a genetic optimization algorithm, MOGA2, was chosen to address, to solve this problem. We can get to the results. On the right side, you can see the an example of 3D Pareto designs. In that case, we have on the x-axis the efficiency, on the y-axis the current density, and the color represent the cost for our product. But you can obviously analyze also multi-space Pareto design, so more than 3 dimension, let me say. From the Pareto design that represent the set of optimal, of best compromise design for our multi-objective problem, a most promising design has been extracted and then validated in laboratory by experimental test. And as you can see from the table on the left part of the slide, all efficiency for a different size, for a different power of the electric motor has been improved, and now the new efficiency value is exactly respect the North American regulation, the North American certification. At the same time, we can also we can also reduce, let me say, the cost reduction. The cost reduction has been roughly reduced for a different sizing from 4 to 10%. That is a really interesting results for Bonfiglioli. Coming to the conclusion, and just to summarize what we have seen, the design optimization approach, the multidisciplinary design optimization approach, provided satisfactory results, which were confirmed by the prototypes tested in laboratories by experimental test. It was possible to reduce the weight of the active parts and therefore of the cost compared to the previous series. And furthermore, the optimization process and let me say, the methodologies and the tools developed to analyze, to set up the multidisciplinary optimization process have proved to be so robust as to push Bonfiglioli to use this approach extensively on all other product line. Last but not least, through the automation introduced by the optimization approach, by the MDO approach, it has been possible to explore a huge number of designs unthinkable with manual approach, eliminating the human error. So this is more or less, that's all. If there is some question, I'm absolutely available, but you can also send me question offline after the webinar if you want. Thanks again for your attention.
Good morning to everyone. Massimo speaking from EngineSoft. My presentation is about spray cooling for high power density drives. So let's start from the motivation. So the first aspect, the idea is shown is in this chart. So what you see is the continuous power density and the predicted trend for the next years. And what you see is that between 2020 and 2025, so in the next 5 years, there should be an increase in power density from 4 to 7 kilowatt per kilogram. So this means also almost double the power density of the e-drives. And at the same time, that there should be a quite important growth in terms of efficiency. And cooling of the e-drive is quite important both for the efficiency and for the life of an e-drive. That's why cooling is a crucial factor, and it's something that is under development from many automotive and the engineering companies. An important aspect is that external cooling by water jacket, by air, cannot guarantee proper heat removal for this kind of power density, high power density e-drives. And the reason is quite simple to understand. The power is generated and has to be dissipated at the center of the e-drive, while the coolant flow is on the external side. So the cooling efficiency cannot be high. So the best way to remove the heat is to bring the coolant in the area where the power is generated, and this is the core of the e-drive. That's why running wet e-motors and spray cooling are currently used or under development, as I mentioned before, from different companies. The idea of using simulation is not to substitute real prototypes, but to complement and to optimize the design of the e-drive when it's possible and when it is more efficient to optimize. That is at the early stages of the design process. So the idea is to use simulation, fluid dynamic simulation, and temperature prediction at the early stages of the design, starting from the CAD before building any prototype. What we suggest to do is to study the coolant flow, internal coolant flow in the e-drive, heat transfer phenomena, and prediction of temperature, average temperature, local temperature, and the hotspots. But before finalizing the design and the prototype and going to the prototyping, what we do is to, based on the previous results, based on the original design, optimize the system, working on the geometry, working on the flow rate, the oil flow rate distribution, on the operating condition of the system in order to minimize the hotspot and have a temperature that is as uniform as possible and as low as possible on the critical part of the e-drive. How do we do this? We basically do CFD simulation with meshless methods. The reason why we use meshless method is because it's much simpler and faster. So it allows and enables the optimization of this kind of system. I will give you an idea of the simulation time with a meshless methodology at the end of this presentation. And what you can do with meshless CFD simulation is the oil flow rate distribution, the study of the oil flow rate distribution in the rotor shaft. You can simulate the airflow and the oil flow in the complete system, in the complete e-drive. You can calculate the heat transfer phenomena and the heat transfer coefficient on the entire system, on all the walls of the system, rotor, stator, casing, and obviously windings. And you can transfer this kind of information, the HTC map, to FEA tools to simulate the temperature, to calculate the temperature, and predict also the stress and the NVH of the system. This is a summary of the process. So what we do is to simulate the fluid, all the fluid aspect of the e-motor by meshless CFD simulation. We take the heat transfer coefficient and we map to an FEA thermal analysis to predict the temperature. What you see here is an animation showing moving particle simulation, the oil in the system. In the background, you also see the air mass. And this is the final results that we aim for, the finite element analysis and temperature distribution. Few words about the methodology, the meshless CFD methodology. We talk about Navier-Stokes solver. The name of the software is ParticleWorks. It's based on a Lagrangian method to solve Navier-Stokes, and it can both solve for the air and oil flow, so multi-phase analysis, including the heat transfer phenomena. One of the main applications, as you see here, is lubrication analysis, oil splashing analysis, but I will show you an application in the e-motors sector. If you're probably used to finite volume CFD, so one slide to explain and to give you an idea of how it compares, how MPS, moving particle simulation, compares to finite volume method. Finite volume method, it's based on it's a mesh-based approach, so Eulerian approach to solve Navier-Stokes. You basically have a static or a fixed mesh, and let's say the two main factors affecting the complexity and the computational time, but also the numerical stability of this kind of method, it's when you have moving parts, multi-phase flow at the same time, and in transmissions, you also need to have the forming mesh or overset mesh that are usually complex to build, complex to converge, and this increases the computational time. All these kind of problems that are typical of e-drives and transmission system can be totally removed from the process using a Lagrangian approach. Lagrangian approach basically means that you discretize the fluid by particles instead of cells, and you calculate the trajectory of every single particle, accounting for the interaction between the particles. So you account for the energy transfer, for the momentum transfer, and you can solve the velocity, the pressure, the temperature, and turbulence of every single volume of fluid. These are the main applications, as I mentioned before: transmissions, lubrication analysis, engine, internal combustion engine lubrication, gradability analysis and piston cooling, and e-drives, spray cooling. This is the today's topic. And there are other applications that are related to water management, rain simulation, and other kinds of viscous flow, highly viscous flow, or hydro turbine and mixing. But let's focus on e-drives. The material I will show comes from Ricardo. We ran a simulation, a test case with Ricardo about the e-motor cooling and validation. Here you see the people, the face of the people who worked on this test case from Enginesoft Italy, Enginesoft UK, and Ricardo. And the test case, the aim of the test case was to compare the predictions from ParticleWorks in terms of temperature at different locations with the available experimental data. This is the real system, the real e-drive. You see the complexity, the geometrical complexity of the system, and this is a summary of how it works. The red arrows show the oil path and the oil distribution system. There are 4 nozzles and jets on one side, on the drive end of the shaft, and on the free end of the shaft. And there are 4 jets, 4 rotor jets, and here you see the path of the oil flow inside the rotor. So one of the aim of the oil flow was also to remove it from the rotor itself. And this is a summary of the workflow. The first step was to run 3 simulations, 3 CFD simulation. The first one to calculate the flow rate distribution in the rotor shaft. This is the system seen from the fluid volume. The second step was to calculate the windage effects when you have 10, 16, 20 RPM. It's important to account for the windage effects, the air influence on the oil flow. And the third part was the real oil distribution calculation, the jet impingement on the windings, and the heat transfer coefficient calculation. In short, these are the results of the oil flow rate distribution in the channels. Here you see the computational domain and the velocity field in the channels. These are the nozzles, and this is the flow rate distribution between the different nozzles, rotor and the shaft nozzles. So this was the first simulation and first output. This kind of output is the input for the next model, that is the oil flow distribution in the e-drive. But before running the oil flow, we have to run the airflow. With this kind of methodology, what we do is to decouple the airflow from the oil flow. We do a sort of one-way interaction between the air phase and the liquid phase. And the aim of this kind of decoupling is to make the simulation process much faster. What we do is to run first a single phase simulation with air particles and coarse resolution. This is the results, so the air distribution and velocity in the system. We average the airflow and we export and then re-import the steady state airflow for the second simulation, that is the oil flow. The reason why we decouple is also because we need and we want to have a higher accuracy on the oil flow simulation to be able to predict in an accurate way the heat transfer coefficients. So lower coarse and lower accuracy and faster simulation on the air side, much higher accuracy on the oil flow. So in this way, we account for the airflow effect on the liquid, and this is the final result. This is the oil flow distribution in the system, the impact and accumulation in the windings area, and the flow to the outlets. Here you see the two sides of the same simulation and same e-drive. So this is the third part, the final part of the oil flow simulation. What we do then is to map the heat transfer coefficient distribution on the surfaces, on the walls of the e-motor. This is the map, the averaged map between 2.7 and 3 seconds. So the oil tends to stabilize in 3 seconds, 3-4 seconds. When we have a stable flow and HTC, we stop the simulation, we map, and then we transfer to the thermal analysis that is done with an FEA solver that predicts the temperature. The temperature prediction in this case was done with FIRS 20.2 from Ricardo software. So this step was done by Ricardo directly. And the model, the FEA model, included only the stator components and the windings because the temperature measurements were only available for these parts. When Ricardo transferred the HTC value, did some modifications to the HTC in order to account for the windings insulation. So they simply modified the heat transfer coefficient to account for the thickness and the thermal conductivity of the insulation layers. The heat sources in the FEA model were defined according to the experimental operating conditions, so power distribution from the experimental data, and the temperature was monitored at 6 locations. The final aim was to compare measurements with the simulation. We don't have the absolute values, but we only have the temperature difference between simulation and real data. And Ricardo was aiming for a maximum delta of ±5 degrees. What was achieved was a maximum difference of ±2.8 degrees. And this is these are the 6 thermocouples and the delta temperature between experimental data and simulation results. And as you see, we are always within plus minus 3 degrees. So a very good match. And the model was considered as validated and accurate by Ricardo. Some additional output from this kind of simulation, from the oil flow simulation in the eDrive, by keeping a low particle size, so very small particles to be accurate, we can also predict the air gap pollution, so the amount of oil and the area of the air gap where you have oil. And this is a chart that can be output from the software, where you see the oil volume in the air gap and the trend. After 3-4 seconds, it tends to stabilize. Conclusions, and then we leave space for some questions if there is any. So it's quite clear that for e-mobility, high power density e-motors are crucial, and that cooling is one of the most important aspects. To shorten the development time is critical to be able to simulate, and to be able to simulate in an efficient way. So not simulations that last weeks, but simulations that takes a few days to run. And that's the reason why we decided to use, Ricardo decided to use meshless CFD techniques to compress the modeling and simulation time to maximum 1 week. And this is the starting point to optimize the cooling. Thanks for your time and attention. If you have any question. Yes, there is one question about solving the energy equation. With particle works, you can solve the energy equation. So you can account for heat transfer between the oil and the surrounding walls. There is one question about if the simulation doesn't align with the live testing. We have done a number of validations. Let's say that one of the main factors affecting the accuracy of this kind of simulation is the particle size, as I mentioned before. So when there is misalignment between numerical results and predicted temperature values, for sure we look at the particle size, that is the level of accuracy of the simulation. And yes, let's say that this is the main factor. But we have best practice that then we can give a good starting point and good advices for this kind of simulations.
So, hello everybody. My name is Benoit Bosquebian, and yeah, I will take the last presentation for today. So we've seen a lot of stuff today, and I hope you have a little bit of patience and you are still interested in the last presentation. Okay. We've seen in the previous presentations that there are a lot of challenges to model an electrical motor. So to get some accurate results, we have to model quite a lot of physical effects. For example, the flow field and the thermal effects in the bodies of the electromotor. So that's why we need to carry out multi-physics simulation. But as Massimo said, we also need to get quick results, because we don't want to do simulations which last something like 2 or 3 weeks or even more. So in the next 15 minutes, I will show you some different tools you can use to optimize the velocity or the duration of the simulations. So we'll start with a short introduction, and then we'll talk about 3D CFD, but only a short time, because we already said quite a lot about this. And then we'll jump to the heart of this presentation, and we will talk about 1D CFD with Flonex. So I will show you how to generate a model for an electrical motor in Flonex, and we will see how efficient this thing is. So first of all, we said that we need to do some multiphysics modeling. So we need to model quite a lot of different aspects in the flow and in the thermal effects of the motor. So it means you have to deal with turbulent flows, you have some rotating parts in the motor, and of course you have small gaps between stationary and rotating parts. It's for the flow. On the other side, you need to model the heat transfer quite good if you want to get an accurate prediction of the temperature in your motor. So it means you have to deal with forced convection, you have to deal with free convection, and you have to deal with conduction in the solids, so in the copper and in the iron, and maybe you have to deal with radiation. And on the other side of the slide, you can see the requirements. I think it's clear for everybody. You need to get some accurate results and some reliable results. But of course, you need some fast simulation because you want to get the results quite quick in order to reduce your development time. So the first way to do a simulation, of course, is to do a 3D simulation. So as Bastian explained, and also Massimo, is quite a long way to do it, and you need quite a long time. You have to prepare your geometry first of all. So a lot of details have to be simplified to be able to do a flow simulation. Then in the second step, you need to do the mesh generation for this model. And because you have a lot of parts, rotating parts, stationary parts, small gaps and everything, the mesh generation can be quite challenging too. In the third part, you have to define all the physics, so which temperature, which heat sources, which heat losses, and so on, which materials for all the bodies. So this step is quite challenging too. Then of course the fourth step is quite okay for the user because the computer is computing the simulation or computing the solution, and typically you need something like several hours up to several days or maybe 1 week for very large geometries, and at the end you get the results of the simulation. So the big advantage of this approach, of this 3D approach, is of course you have a very, very good accuracy. But the major drawback is the time, of course. So you need quite a long time. So typically for such a loop, when you start with the geometry, maybe you need something like 1 or 2 or 3 weeks until you get the results. So it's quite a long time, and so maybe you can do this for one operating point, but as soon as you want to do several operating points, or if you want to do some stuff like startup of the machine, shutdown of the machine, or to have a look at transient effects, then of course you have a problem because you don't want to wait for the results like 2 or 3 weeks or maybe some months. So that's why the idea to reduce the cost of the simulation and the time of the simulation is to try to do a 1D simulation. And for that, you can use a software which is called Flonex. And Flonex is a CFD solver which solves network models to calculate pressure losses, mass flows, and heat transfer for fluidic and thermal systems. The big advantage of Flonex, it's a 1D software, but it's a CFD solver. So it means it solves for the conservation of mass, momentum, and energy. You can use incompressible and compressible medium. You can have some gases, you can have some liquids, you can have some mixture of gases and liquids, and you can also have non-Newtonian liquids. You have single and multi-phase flows. You can do in the same user interface, you can do a steady state simulation or a transient simulation. And a big advantage of Flownex, you have a lot of integrated coupling to a large number of other codes, like, for example, ANSYS and Excel and MATLAB, and also many more. So it means you can easily couple the 1D simulation in Flownex with a 3D simulation in ANSYS, for example. What kind of libraries do you have in Flownex? The major libraries you need for the modeling of an electrical motor are shown on this slide. So first of all, you have a big library for heat transfer. To be more accurate, actually, you have two libraries. You have a library for heat exchanger. In this library, you have some different type of heat exchanger, but maybe for us, the better library is the library heat transfer. So with this library, you can model some different kind of heat transfer. So for example, the conduction in solids, the convection between solid and air, but you can also model a combination of both with a composite transfer. You can model some heat sources, and of course you have some components, of course, for radiation. The second big library is a piping library, so you can define some channels, and you can see the rotating components at this position. And of course, in an electrical motor, you have a rotor, so you need also some components which take care of the rotation into account. And here, so you have some rotating channel, you have some cavities between a rotor and stator, or between two rotors, so you can model all this stuff with these components. If you have a look at an air-cooled motor, you need a fan, for example, for the air. So you have here some fans, or if you have some water in the casing of the motor, you have some pump to be able to pump the water or the cooling medium to your motor. And of course, what is really important are the coupling components. So you can couple to CFX, to Fluent, to Mechanical, you can use Excel, and you can couple to other software, as you can see there. And with the scripting component, you can couple to every other software you can think of. Moreover, or in addition to these libraries, you have a lot of tools which help you to carry out a fast simulation. So for example, you have the optimizer and the designer, so you can define some values very quickly. You can do a sensitivity analysis in order to investigate the impact of design uncertainties. And as a big advantage of Flownex, you also have a transient solver. It's in the same user interface, so it means you don't have to switch the model between stationary and transient. You can do everything in the same window. Yeah, so you can define some actions, for example, what's happening when the pump is shutting down, or when the fan is not working anymore, or when the power is getting higher, or stuff like that. And you can see how the system is reacting. You can, of course, visualize the results, and you can use Excel and scripting to add new physics in the software. So let's have a look now at a model for an electrical motor. So what you can see you can see the rotor at the bottom. In this part, you can see the stator with the copper and the iron. You can see the fan, which is on the right-hand side of the slide. And you can see the different flow passes. So you have a flow pass at the top between the iron and the casing. You have a flow pass at the bottom. These are the rotating channels through the rotor. And of course, you have this small gap between the rotor and the stator. And what you need in Flownex are different components to model all these passes. But actually, you have everything you need. So you can see we use some distributed heat sources. So with these ones, we can model the heat sources in the iron and in the copper. And in the same time, in the same time, you can model the conduction within these bodies, and you can model the convection to the cooling air. And if you want, you can also model the radiation between the different parts of the model. Then we have a rotating annular gap. With this component, we can model the very small gap between the rotor and the stator. We have the rotating channel for the channels in the rotor at the bottom of the geometry. And what we've done here, you can see some Excel sheets in the model. So we use these Excel sheets to parameterize the model. So in the Excel sheets, you can define the volumes and the lengths of the different bodies. And you can also define the cross section of the gap between rotor and stator. So it means if you want to have a new model, you just have to change a few numbers in the Excel sheets, and then you can compute the new solution. So as you can see there, you have something like 20 components only, and so it's quite it's quite fast to do this model. You can see here some boundary conditions. So you have to define the rotating speed. For this example, it was 1,200 revolution per minute. Then you have to define the conditions as the inlet and outlet. So for this example, it was just 1 bar and 25 degrees. And then you have to define the heat losses in the different parts of the motor. So these heat losses, they are just defined as a parameter in the different Excel sheets. Then you have to define the fan curve or the fan map for the fan, which provides the air in the motor. And then the big point, or the very important point, in order to get accurate results for the simulation or for the temperature, you need the heat transfer coefficient between solids and air, and you need the pressure losses in the inlet and outlet domain. And at this point, you have several possibilities. Either you have some correlations of your own, and then you can define them very easily. In all these components in Flownex, you can use the components which are provided from Flownex, or you can define your own components or your own correlations. So it's the first idea. So if you have some correlations you validated already, then you can use them. Maybe you can just get some correlations from the literature, from some articles. If you don't have anything, then maybe you have to do a 3D simulation with ANSYS CFX, for example, or with ANSYS Fluent, or with something else. So in this example, we've done it with ANSYS CFX. So for one operating point, we did a simulation so that we can get the heat transfer coefficient. For the pressure losses in this domain, in the inlet domain and in the outlet domain, of course, the flow is quite 3D at this position. So it means with the 1D correlations you have in Flownex, maybe you won't be able to get the right pressure losses. So it means we use the 3D simulation to calibrate the pressure losses in the inlet and outlet domain too. Yes. Okay, so maybe now you will ask, okay, if you do a Flownex simulation, but to be able to define the model, you need a 3D simulation. Yeah, is it worth something? Yeah, I would say to answer the question, just let's have a look at the computational requirements and the computational times. If we have a look at the main memory, for the simulation with ANSYS CFX, we need something like 50 gigabytes. So it's already quite a lot. If you have a look at the simulation with Flownex for the 1D simulation, you just need something like 1 gigabyte, probably less than that. So yeah, you would say it's not a big problem because everybody has a big computer now. But if you have a look at the simulation time, so in ANSYS CFX, just the simulation time, you need something like 1 to 2 days for the simulation. If you compute the same solution in Flonex with the model I've shown you, you need, and it's not a joke, you need 2 seconds. So of course you can see at this point the big advantage of Flonex. So the strategy here was to generate a model with Flonex. In order to validate this model for only one operating point, we did one 3D simulation for this operating point so that we had a good model. And then, of course, with this validated model, you can do some other simulations and to calculate some other operating points. Or maybe you want to change the geometry a little bit to see how big the influence is. And of course, if you do this simulation with ANSYS CFX, you need several weeks to do all your simulations. If you do this with your validated model in Flonex, you need, yes, maybe like 1 hour for, I don't know, 20 operating points or maybe more. Yes. So just to show you this method is really working, we have on this slide, we've calculated 3 operating points with Flonex, with the Flonex model, and also with a 3D CFD model, just to check that everything works as we expected. So on the left-hand side, you can see the rotor temperature, and on the right-hand side, you can see the temperature in the stator. And so you can see that you don't have any difference in the temperatures between the Flonex model and the CFX model, or it may be something like 0.2% or something like that. So if you compare the computational times and the accuracy you get, of course, it's really a big advantage to use the 1D simulation. Okay, and actually I'm already at the end of my presentation. So just as a summary, in this project, we generate a very simple model for a very complex geometry for a motor in the software Flonex. The geometry and the heat losses were parameterized with an Excel sheet. The heat transfer coefficients, which are very important for the accuracy of the simulation, they were computed with a 3D simulation, but only for one operating point. And the pressure losses, they were also calibrated with the same 3D CFD simulation. And then in the second step, we could carry out a lot of simulations with a calibrated model, and yes, a simulation with a 1D model lasts something like 2 or 3 seconds. And of course, at the end, yes, the results are exactly the same with the 3D and the 1D simulation. So it's really a big advantage for the computational engineer to use this method. Okay, thank you very much for your attention. And yes, I hope you enjoyed all the presentations. And if you have any question about this one, of course, you can contact us or contact me. Thanks a lot.
Okay. You have a question on the question panel?
Okay, just leave.
Do you see it?
Yes, I see
Okay.
it. I just have to do it larger so that I can read it. So the question is, can Flonex handle phase changes and real gas law? Phase changes, you can do it in the library of Flonex. In the database, you have a single flow, so liquid or gases, but you also have two-phase flows. So all the common flows, you can find them, and they can evaporate and they can condensate. So it's not a problem to do it. Actually, Flonex is comes from the power plant application, where you have some boiler and some condensators and everything. So a two-phase flow is not a problem in Flonex. And for the real gas laws, you also can implement them. You have a lot of interfaces to different database, but you can also for the common fluids, you can also use a real gas law for the common fluids.